In this video, we'll discuss some applications of logic. First, let's discuss logic gates. Now, it turns out that logic is used in computer hardware design, and we have gates that represent the logical operators. So an inverter gate is for negating its input. So for example, if you have a bit passed to an inverter, the bit that comes out is the negation of it. Now an OR gate is given two inputs and calculates the OR. An AND gate, the AND of two bits, and the exclusive OR gate, the exclusive OR of the input. Let's see how these are actually used in an example. Suppose we have a sensor network, and in this sensor network we have 3 sensors, and we want the network to send true to a control station if at least 2 of the sensors are set to true or sending true signals. So in order to create a logic circuit that meets these requirements, we would have to have our 3 inputs, and we would have to check the logical AND of the 3 pairs of those sensors and then take their exclusive OR. So let's see what this looks like. So we are going to have to do the logical AND 3 times. And the input to the AND is going to be the input from the sensor. So we have our first sensor, so I'm going to call this sensor 1, and then we have sensor 2, and we also have a third sensor, which we will call sensor 3. And so first we take the AND of the first 2 sensors, and then we have to also take the AND of the second and the third sensor. And what we can do is, if either of those ANDs are true, then we know that we satisfy the requirement. So here we can take the output of both of those AND gates and send it to an OR gate, because if either of those pairs are true, then we know we've satisfied the requirements for the system. But now we also have to consider, so we've considered S1 and S2, then S2 and S3, but we still have to consider S3 and S1. So I'm going to draw a line here, and usually there is a little bit of a curved line when you're crossing the wires, but I'm not going to put that. Okay, so I'm taking the AND of S1 and S3 now, and I can take the output of this and OR this with the output of the other gates. And when I do that, I can send the signal to control right there. And so let's just make sure that we are meeting the requirements. So this first gate right here is calculating S1 and S2. And the next gate is calculating S2 and S3. And we can see that this first OR gate is taking the OR of those. And then the last gate is checking S1 and S3. And we're just taking the OR of that input with the OR of the previous one. So as we can see, if at least 2 of those sensors are true, then the entire circuit will return true. You can also verify that if at most one of the sensors is true, this circuit would return false. Now let's consider another example. And in this example, we want to create a half adder. That's a logical circuit that adds together 2 bits. And it should have one output bit and one carry out bit. So we have 2 bits that we want to add. Those are X and Y. And we need to think about what happens when we add 2 bits. So when we add 2 bits, if both of the bits have the same parity, if they're both 0 or they're both 1, then the resulting bit should be 0. And if their parity is different, so if X is 1 and Y is 0, vice versa, then the output bit should be 1. So that is indicative of using an exclusive OR gate. So I'm going to draw my exclusive OR gate. So this is going to create the output bit. But now I have to worry about the bit that is going to be the carry out bit. So now I have to think about, well, what should happen in terms of whether there should be a bit carried over. So if both X and Y are 0, then there's no carry out bit. And similarly, if they have different parity, there's no carry out bit. So if both X and Y are 1, there should be a carry out bit. So now that means to figure out the carry out bit, we need an AND gate, which should be set to 1 if and only if X and Y are 1. So now I can draw that. And that will be our carry out bit. And now we can verify what happens with this. So if both of our bits are 0, our output will be 0, and our carry out bit will be 0. If X is 1 and Y is 0, our output bit will be 1 from the exclusive OR, and our carry out bit will be 0, and vice versa. And finally, if both X and Y are 1, our output bit will be 0 because the exclusive OR of 1 and 1 will be 0. But now, in the AND gate, the carryout bit will be 1 and 1. So we'll have the 1 bit carried out. And our output bit is basically the sum bit. Now, let's look at some examples of translating natural language to propositions. And as a caveat, I just want to mention that sometimes we are not as precise when we speak English as we are when we use mathematical notation or logic. So some of this is just practice and interpretation. So first of all, there are many ways of saying an implication. So there's P implies Q, if P then Q, P is sufficient for Q, Q if P, Q and P, a necessary condition for P is Q, P only if Q, a sufficient condition for Q is P, Q whenever P, Q is necessary for P, and Q follows from P. Now, it's not so important to get too overly concerned about these. It's just to bring your awareness that there are many ways in the English language in which we may want to convey an implication. And I also want to mention that sometimes when we speak in English, we are not as precise as we may be if we were just giving a logical proposition using mathematical notation. So this is just a little bit of a warning, but let's give some practice anyway. So we're going to convert the following statements to logical propositions. So roads will be wet if it rains. So that's Q if P. So here our premise is P, it rains, and our conclusions will be wet. So if it rains, roads will be wet. You can only pass the exam if you study tonight. So here, our premise is pass the exam. If you pass the exam, then you study tonight. That's P only if Q. Now, we can think of a very common problem that we have in the language is determining between or exclusive or, because when we speak we're not always so precise. But first, let's talk about the conjunction in English. So it is below freezing and snowing. So in this case, we can say P is below freezing and Q is snowing. So P and Q. And I just want to mention that the other examples are examples of just implications. Now we have it is either below freezing or snowing, but not both. So this is a little bit awkward because in English we probably would not say that. We'd probably say it's below freezing or snowing. But when you see the language, it is either below freezing or snowing, but not both, this is meant to indicate that we mean exclusive or. So that's what I meant. Sometimes this is quite awkward when we are translating English into propositional logic, or we want to indicate precise logic. And another very common misuse of language, or sort of natural language, is if and only if. Sometimes when we have implications in English, we might say, if you complete your chores, then you'll receive an allowance. But we actually mean if and only if, even if we just phrase it as an implication. So I just want to give examples of how we can translate language to logical propositions, but I just want to give the warning that oftentimes we need to be a little bit more precise when we are using logical propositions.